So good morning, and today I have quite a little bit of a complex topic to tell you, but I will try to make it as simple as possible. I am talking about risk-based design for space systems. The question that many ask is how it is possible to make a completely new space system safe when we know nothing basically about the architecture, the configuration, the way the system will be designed and built. I will explain to you that there is a technique which is called risk-based design, which allows us exactly to do that, to embed into a new design safety. To clarify, a little bit the overall concept, and then we will go into, the various steps. Think about an accident, an high visibility accident, an aerospace accident, aviation, an aircraft, an airplane that crashes. Usually, after an accident like that, there is a committee that will investigate the accident to determine the root cause of the accident. Okay. They will look into, data, design, operation, and eventually they will most probably find the root cause of the accident. Now, you could guess that if the same committee had investigated the same kind of design with the same data, etc., before the accident, they may have spotted the condition for an accident into the design, and probably more than one condition, several possible conditions that could lead to an accident. This potential condition leading to an accident is what we call technically an hazard. Okay, so whenever we do an investigation of an accident after it happens, we are talking about an accident investigation. When we are investigating the potentiality for accident before they happen, we are doing an hazard analysis. You will understand that when things have not yet happened, there could be a number of additional information that needs to be provided to the investigators. One of this information is about what is considered let's say, a credible event. A truck can take fire in the middle of a road because overheating of the brakes, but it could be exceptionally also take fire because there is, a lightning strike exactly on top of the truck. Of course, the credibility of these two phenomena to happen depends very much on the probability. So we have, first of all, make sure that the condition, the event that we consider into an hazard analysis are credible. On top of this, we have to put a limit to the recommendation that we have to make about a safe design because, there is potentially no limit about what you can ask to achieve safety. But safety is not something absolute. Safety is relative. There is always a level that you achieve and you should consider acceptable. So there should be also information about where to stop with your recommendation having achieved what is considered an acceptable level. So this is basically what we are talking in risk-based design, analyze a design as it develops, as it matures, and identify the hazard into it, make recommendation to remove the causes of this hazard, and stop with this recommendation when a certain acceptable level of risk is achieved. Having said that, we will progress now through my presentation, which will I try to make, as simple as possible, but still I need to provide you certain key, let's say, information. Again, here we see the definition of an hazard, which is a state or a set of conditions. So an hazard is not something, but it is an event, an hypothetical event. Then what is an accident? An accident is an hazard becoming actual. And what is a risk? A risk is the probability that a certain condition become, actual, such that the hazard becomes an accident. And as I said a few moments ago, safe is not absolute safety, but it is an acceptable risk level. What you see in that picture is a pot of flower, which an old lady accidentally, pushes out of the balcony. And in one case, there is a loss of the pot because it will crash on the floor. On the other case, there is a poor guy passing beneath the window, the balcony, exactly in the moment in which the pot is falling. And here we have basically another scenario, another accident. Although the initial conditions are the same, these are two different hazards. And you see that the probability of this to be an accident is the probability that the lady will push the pot and the probability that the guy will be just beneath the trajectory of the pot. These are called causal factors. So the causal factors will determine the probability of the event. A quick clarification. I will not go through all the content of this slide, but just to tell you that we use very much in space safety design the term failure and fault. The two terms have a different meaning. However, we use them almost everywhere as interchangeable terms. In particular, failure refers to an event, while fault refers to a condition. The condition could exist before the failure, a software fault, for example, or could be the result of a failure. So after a failure, there is a fault condition of a system. Now, as I mentioned, an hazard is not something, but it is an event, okay? So an hazard depends on the context. You see here a knife. The knife itself is not an hazard. It's what we call an hazardous element. Now you need a certain condition around this hazardous element to have what we call an hazard. This condition is, for example, a young boy playing with the knife inside the power socket, or a young girl trying to cut, some food. One could be killed by electrocuting, the other could be injured, etc. And then, of course, we use every day a knife as a part of our cutlery, and we can damage the plate, do something other. kind of damages that have no truly value, are not truly hazard, are marginal hazard, so non-hazard if you want. It is very important to keep in mind that our analysis, our hazard analysis is oriented, is focused on removing root causes. However, in the description of the hazard, you identify usually the proximate causes. The boy being electroshock while playing with knife and power socket. In this case, the electroshock killing the boy is the proximate cause, and the root cause is about the accessibility of live contact to a person who is not completely aware of the risk. So we have to keep in mind that in performing an hazard analysis, we are aiming to remove root causes. However, in the description of the hazard, usually we describe the proximate cause of the hazard. Behind an hazard, there is always some sort of failure or fault. However, it is useful to differentiate different type of hazard causes. The one that we have to identify and mitigate as being of three kinds: functional, inherent, and induced. A functional failure of a safety critical system is for example, for an astronaut on orbit into a pressurized environment, the loss of pressurization, the loss of the system that provides pressurization is a safety critical functional failure. And this is one kind of hazard causes. The other is so-called inherent hazard causes. There are on space system usually toxic compound, flammable materials, sometimes also radioactive materials, part of experiment, for example. So there are various cases in which, let's say, dangerous element or even extreme temperature, etc., happen. This hazard causes needs also to be investigated to identify if there are conditions such that there could be a leaking of toxic compound or that could be flammable materials, etc. Finally, there is a category of hazard causes, which are the induced causes. The induced causes is a very, let's say, strange cause, if you want, because it is about those causes which exist because people have not applied the necessary knowledge, skills into the design. So basically, a design error for something which is notoriously required is considered, an induced hazard cause, and into the investigation of a design, we look also to prevent that, certain design errors or manufacturing errors are made. These are the hazard causes which we want to remove. Here, some further details about functional hazard causes. There are two kinds of functional hazard causes which we considered important to differentiate, which are must work function and must not work function. An accident could occur because a function does not activate at the right moment. A parachute not opening at the right moment is a must-work function which fails. There are also cases in which an accident happens because a function is activated at the wrong moment. This was, for example, the case of the accident in 2014 with Spaceship Two, where the rotation of the so-called Fager system, that is the tail system of Virgin Galactic Spaceship Two, the untimely rotation caused the crash of the vehicle. So that rotation was done at the wrong time and constitute the cause of the accident. Inherent causes. An angry lion is an hazardous element, and if the condition arises that you can get in contact with an angry lion, then you have an hazard. So you have the potential for an accident. Now, this is the meaning behind inherent causes. Please note that the hazard itself is always deterministic, is there or is not there. What is probabilistic is about the causal factor that may exist, such that, that the accident happened. Induce hazard causes. If you use pressurized atmosphere of oxygen with flammable material and some combustible fuel, etc., you have the condition for a fire. And this is what happened with the Apollo 1 accident in 1967. So the Apollo accident, that was, by the way, an accident which happened on ground, was due to induced causes. So was due to the fact that a faulty design had been put in places, not because there was a threat from outside. The design itself, notoriously at that time in many fields, the use of pressurized oxygen, pure oxygen, was very much treated with a lot of cautions, etc. At NASA at that time, there was no safety program, there was no safety analysis, there was no risk-based design, and an accident happened. It was after this accident that NASA established the rules and the requirement for performing risk-based design, exactly after this accident. Another means to help you, let's say, understanding the hazard and how you identify the various elements and where to act, is to think in terms of so-called hazard triangle. The hazard triangle are the three elements which make an hazard happen. And these three elements are an hazardous element, an initiating mechanism, and a target. I like this picture because it shows you a little bit the three elements at work. You have a cat, the target. You have the owner of the cat playing with a loaded gun. Inside the loaded gun, the hazardous element is the bullet, okay? And then by some chances, some mistake, etc., the gun could fire when the cat is exactly, on the trajectory of the bullet, and the poor cat is is killed. So the hazardous element is the bullet. The initiating mechanism is the gun with the owner triggering the gun, and the target is the cat. Now, this simple example can be very much used to help you identify the component of the hazard, where to act to, let's say, increase the safety, decrease the probability of an accident, etc. Here, in this slide, I make an example of more, let's say, related to space, saying that during maintenance of a certain equipment on board the space station, the astronaut is electrocuted by touching a live high-voltage electrical terminal. This is the description of the hazard. And you see that high voltage is basically the hazardous element, and the initiating mechanism is the touching, and the target is the astronaut, and it is the probability of the astronaut having access to the area where these live contacts are in a moment in which power should not be there, but inadvertently has been applied. This created the probability for that hazard to become an accident. So the risk of an accident, there is no risk of an hazard. There is a risk of an accident, which is the hazard becoming actualized. We use very often risk matrix to provide this idea that on one side, the probability of an event to happen and the severity of the consequences of that category, and the two together define what risk is. Risk is probability by severity. The probability that you win at Monte Carlo Casino, but by betting all your money, your fortune, etc., as you know, there is a low probability, but if things go wrong, the impact on your life is enormous. So the risk is enormous. Having identified the hazard causes, now is time for you to start working on putting the hazard under control. As I told you at the very beginning of this short exercise today, you cannot reach absolute safety. You reach a certain level of safety, and there is a level of desirability into the action that you take to reduce, mitigate an hazard. Of course, ideally, the best is to eliminate the hazard, but sometimes eliminating the hazard means also to lose the function, which is essentially for your system, for your equipment. So this is something that can happen, but very rarely. Then what you do, and the priority is by doing so, is to develop design solution that mitigate the risk. If you have difficulty of developing design solution, or together with design solution, you can provide detection and warning, which goes under the category of operational hazard control. Now I tell you, be careful, okay? And you will operate being careful not to cause a problem, etc. And then there is the case in which you can develop a special procedure or training. This is the sequence of desirability of hazard reduction let's say, measures, which is used, I would say, worldwide, not only in space, but is used in many new fields of engineering. This is just a way of recapitulating a little bit what I said up to now. You see the lion, which is the hazardous element, the target, and then we see another guy separated who is transporting stuff around in the circus. And, that is the triggering mechanism, the initiating mechanism. The wheel of the cart squeezing the tail of the lion while he's, doing a quite a tricky exercise. So this is the hazard. You see, the hazard is a condition that is there that could be triggered. Eliminate the problem, cut the tail, of course. No one will do this. Or you create a fence such that even if the tail comes out of the cage, then there will be no way you can squeeze it. And then you can have, sign saying keep clear. So providing information to the operator of the cart to behave in a way of avoiding the condition of the hazard. So to recapitulate, what we call hazard controls are all those measures that we take into the design of a space system to mitigate the risk of an hazard becoming actualized, so becoming an accident. There are two kinds of hazard control: design hazard control and operational hazard control. We talk, a little bit by example up to now, but if we go now in more detail, the hazard control that we use in space system design are barrier and inhibits. Inhibits are basically switches, things that are there basically to cut power, such that inadvertently you will not be, energizing an element, a function in the wrong moment. In this case, you may have multiple switches, safe and arm, prepare and then they trigger, which allow you to make, the right decision with this. There are other barriers that are used in space. For example, for debris, there are special panels which are installed on human spacecraft, crewed spacecraft, which are meant to absorb the heat from space debris and reduce the damages that they can cause to the spacecraft. This is a kind of a barrier. The protection could be external to the human or could be in the form of, mask and other protective equipment that you may think about. Things that are also barrier in space are, for example, filters. You may not know, but because of microgravity, during space operation, there could be, chips from the manufacturing of the system or equipment, metallic chips or fragments tiny fragment of glass, which differently from the case, the ground case, they are floating in space. So in this case, you want to control this stuff. Now, remaining on the topic of controlling the hazard, let's talk about redundancy, because here I wanted to pass you a key message, which is the following. Redundancy are very much used, etc., but most of the people think that the function of redundancy in space for safety is because they increase reliability. Not at all. Very often, the redundancy, is such to reduce the reliability but allow safety. You see in this slide a case of the parachutes of Apollo, and in particular this is the Apollo 15 mission, and one of the 3 parachutes did not inflate. Now to have a successful deceleration of the capsule during the return to Earth, you need just 2 parachutes, but over there were 3 parachutes, because each parachute has a probability of failing. By adding a redundant parachute, you are decreasing the reliability of the system. However, the one that failed was 1 out of 3, where 2 were sufficient. Therefore, you were penalized in terms of reliability, but you were safe, because if you had just a 2 parachutes configuration and one would have failed, like you see in this picture, then the astronaut would have impacted with an high acceleration and probably suffered, injuries or even worse. This is just an example of the redundancy used on various components of a space system. In this case, here we are talking about computers, wiring, solar panels, battery, life support system of Orion, which is the moon capsule from NASA. And the purpose of this table is to show that there are various numbers of redundancy per system, which is very much driven by the nature of the system. For example, the computers on Orion, there are 5 computers, but these 5 computers, 4 identical software and 1 backup with different software, are meant just to reach what we call 2-fault tolerance. And the reason is that when you have just 2 computers, you need a third one for voting purpose to understand which of the other 2 have failed. And if you need to be 2-fault tolerant, you need a 4th computer. And because there is always a risk of so-called common causes, you need then a backup computer. This makes 5. So the criticality of redundancy depends very much on the time to criticality that is related to the operation. There are cases in which, for example, drinking water, you can have a failure of the water delivery machine that you can fix on orbit, because the time to criticality could be perhaps 1 full day. So this is to show that redundancy and the criticalities, etc., they drive the number of redundancies. So there is no fixed rules, depend subsystem by subsystem. The concept of a fail-safe. There are two kinds of a fail-safe system that you need to understand exist. One is passive fail-safe, and the other is active fail-safe. Passive fail-safe is something that when fails, basically the function is still there, but in a degraded, let's say, version, if you want. This is the case of a scuba diver regulator. When the regulator fails, it is designed to fail open, so to deliver oxygen continuously, which of course lead to an overconsumption of oxygen, but gives you the time to go back to surface. The other case is the common case of an airplane. Our airplane nowadays are most twin jets, and the twin jets have exactly the idea that with one engine you can do the complete flight, means takeoff to landing, but you have two jets, and the moment one fails, you have to stop the mission. You have certain time calculated on the basis of certain criteria to stop and go to an airport. But nevertheless, your flight is finished. You will not reach, most probably, your final destination, because the rule will require you to end your flight very soon. Use of design standard. We have been talking about redundancy. We have been talking about credible failure. Now, there are a number of cases in which the technology that we use in space has matured to a level that we can assume that basically the reliability of this system is equal to 1. And this is the case of, for example, structures, pressure vessel, and similar. So when you think about a space system, an innovative space system, the large part of that innovative space system is made of components, battery, tanks, computers, etc., which already exist. So you have to assume that a good part of the technology used are already proven, existing, and you can rely on the knowledge that you have of certain techniques to make your system safe. So it's not that you have to do everything redundant. There are certain cases in which redundancy is already design standard and the safety margins basically fulfill the purpose of high reliability and failure avoidance. Operational hazard control, we mentioned briefly that through alert procedure, pre-planned decision, you can have operational hazard control. So you have the crew intervening to make sure that an hazard is not actualized. Now, let's go back now to one of the final points that I want to make today, and it is about acceptable risk. So what I start saying was that when you look for the mitigation of hazard in the design of a new system, you have to, to achieve a certain risk level, acceptable risk level, and not beyond. What is how this level is defined? Is defined in terms in quantitative terms, like loss of crew probability. So this could be a goal that is given to the developer to say your capsule shall have a loss of crew probability less than 1 in 270 mission. Another requirement that is very often used is so-called failure tolerance, which is a way of imposing, redundancy mainly, as a way of preventing, an accident. Then margins, also these are predefined. And there are many thresholds and margins that are used. Margins for threshold for acceleration, pressure, radiation, contaminants in the air of a capsule, thermal, acoustic, and electrical threshold, that you have not to exceed, and so on. So basically, this acceptable risk level are of three kinds: failure tolerance, failure avoidance, and quantitative risk. So these are given, and these are basically what helps the designer getting assured that he has achieved the required level of safety. Here, just a note of caution: don't consider always failure tolerance to be the synonym for redundancy, because sometimes there are other means like operational hazard control that are used for failure tolerance purposes. This is a little bit a slide summarizing the entire business of failure credibility and what is risk-based design. And basically, I conclude with the following slide to say that risk-based design consists in the identification and control of hazards, such that the system achieves a predefined level of safety by means of so-called hazard controls. Hazard control consists of design solution and/or operational procedure for failure tolerance and/or for failure avoidance, redundancy, or safety margins. Hazard control for failure tolerance aim to mitigate the risk of loss of function while preventing any unwanted system behavior. And what you see there is the picture of the Boeing 737 MAX, which crashed because of a faulty hazard analysis. In the hazard analysis, the functional criticality of the so-called MICAS system was classified only by considering the loss of the function and not the behavior following the loss. And this caused the loss of two airplanes and almost 400 lives. Thank you very much for your attention. A very complex subject, but I hope that I gave you at least one glimpse about how we usually embed safety in modern space system. Thank you.
Thank you, Tommaso. Anybody can type their questions in chat. And we have maybe 1 more minute.
Unfortunately, my audio is almost zero. So I would very much encourage to send any question by mail, and I will be glad to answer.
Do you want to share your email in chat? In case
it's completely lost. I have no audio.
All right, if nobody has questions, then I'm going to end the session. Thank you everybody for joining. We have sessions running throughout the day in different rooms, so please check our website and you can join other sessions as well. Thank you. Bye-bye.